Hello, here we go. We are solving the Spring 2017 final exam from A266. This will be the last 10 questions of the exam, all the stuff related to midterm 2 and then a little bit extra. And we start off with 10, which of the following is a particular solution to this differential equation. So we're going to be solving this using the technique of variation of parameters, but unlike most variation of parameters questions, they don't actually give us the fundamental solutions to start off with. That's because it's pretty trivially easy to find the solutions to the homogeneous equation here, which is given by our characteristic equation, r squared plus 4 is equal to 0, or r is plus or minus 2i. So we see that yc is equal to c1 cosine 2t plus c2 sine 2t. And so our fundamental solutions are just cosine 2t and sine 2t. And with that, since this is already in the form that we like to see with a coefficient of 1 on our y double prime, we can go ahead and apply our formula for variation of parameters, where we will have negative y1 times the integral of y2 f of t over w, the Wronskian, dt, plus y2 times the integral of y1 f of t over the Wronskian, dt. The only thing left for us to do is find this Wronskian. The Wronskian will just be, Wronskian is the determinant of the matrix formed by our two fundamental solutions, so cosine 2t, sine 2t, and then their first derivative, so negative 2 sine 2t and 2 cosine 2t. This will give us 2 cosine squared 2t plus 2 sine squared 2t, which is just 2. So let's replace both of our Wronskians with 2's. This f of t term is just whatever we have on the right-hand side here. So we can delete that and put a cosine 2t. So we have 2 cosine 2t on both of those bottom denominators. And then our y2's will become sine 2t's, sine 2t, and our y1's become cosine 2t's. And we're ready to solve. Our integral on the right is much easier. Our cosine 2t's will cancel. We will have the integral of 1 over 2 dt, which will just give us 1 over t dt. So we get 1 over 2t, not 1 over 2 dt, sine 2t. And we're already kind of sort of halfway done, although this last bit is a little weirder. The integral, we'll factor this 2 out. The integral of sine 2t over cosine 2t. We can do a u substitution. U is equal to cosine 2t. du is equal to negative 2 sine 2t. And that will let us rewrite this as negative cosine 2t over 2 times the integral of 1 over u. And then our sine 2t will get canceled out from dividing out our du. But in addition, we'll still have this negative 2 left over in our denominator times 1 over negative 2. I'll pull this out. We'll have 1 over 4 over here, and this 1 over u du will become the natural log of u. U is cosine 2t, so we're left with y of t as cosine 2t over 4 times the natural log of cosine 2t plus 1/2 t sine 2t, and that is D, I'm pretty sure. 10 is D. 11, we have an electric circuit with a capacitor and an inductor connected in series. The charge Q of t in the capacitor satisfies this second order homogeneous differential equation with some initial conditions. And we are just asked to find this, I think it's termed a phase angle in our syllabus, and R, which is really the magnitude of our oscillations. We know that R, kind of thinking about this in mass spring system land, R is the square root of a squared plus b squared, where a and b are the coefficients on the sine term and the cosine term that we'll see appearing in a second. And then our phase angle, which this symbol comes up in Laplace transforms, and I've been tentatively calling it gamma for a while. Not particularly sure why. It's a lowercase delta. I know that now. It's only slightly embarrassing. So this delta, our phase angle, is the inverse tan, arc tan of b over a. So we can solve for all these things relatively easily. Let's grab our characteristic equation. That's 9r squared plus 1 equals 0, or r squared equals plus or minus 1/3 I. So we can write our QC of t, our characteristic solution, as C1, or I'll say A, cosine 1/3 t plus B sine 1/3 t. Additionally, we know that Q at 0 is equal to 1, so 1 is equal to A times the cosine of 0, which is 1, plus B times the sine of 0, which is 0, so A is equal to 1. Then if we find QC prime of t, that will give us negative 1/3 A sine 1/3 t plus 1/3 B, not sine, cosine 1/3 t. Again, evaluating everything at 0, setting everything equal to 1, we see that 1 is equal to 1/3 b, or b is equal to 3. And as a result, we can go back up and rewrite our QC of t, which is really just Q of t, because we're not dealing with any kind of forcing term on our right-hand side. This will be cosine 1/3 t plus 3 sine 1/3 t. We said that delta, oh, that's a weird delta, is equal to the arctangent of b over a, so b over a is 3, and we said that r was equal to the square root of b squared plus a squared. That'll be 9 plus 1, so root 10. And so we get b for 11. Question 12, a particular solution of this equation is of what form? Right off the bat, we have to solve our characteristic equation. That's r to the 4th plus 2r squared plus 1 is equal to 0. This factors to r squared plus 1 squared, so this will give us r equals plus or minus I with a multiplicity of 2. As a result, our characteristic equation will take the form C1t cosine t plus C2t sine t. And those t's are appearing because, remember, we have to multiply everything by t when we have a multiplicity of anything greater than 1. So we are ready to go here. We see that in our term f of t over here, we would like our guess for y particular to be a cosine t plus b sine t plus 2 e to the negative, not 2, c e to the negative t minus, don't know what it is with me today, plus dt plus e, but this isn't going to work. We need the power of t multiplied by our sines and cosines to be greater than anything here, because remember, if we were to take this yc and split it up like we do when we're finding our guess for using undetermined coefficients, like how this 5t becomes dt plus e, the guess related to these would be a t cosine t plus plus b cosine t. You need to split up that t into something multiplied by t and something multiplied by a constant. I don't think I'm making much sense here, but essentially all we need to do is multiply these by t squared, and we are out of the woods, and that does lead us to option D. 13, we have a spring system with an external forcing term, and it's represented by this equation. We're looking for the steady state solution of this system. So the steady state solution is the solution given by x particular, or in this case y particular, and we can solve for that using undetermined coefficients. And just vocab review, the steady state solution is a solution that kind of takes over time from the transient solution before the system kind of reaches, I don't want to say equilibrium, but a more regular pattern of motion. So we have to solve our characteristic equation first in order to figure out whether or not we have to multiply our guess by any amount of t. So r squared plus 2r plus 2 is equal to 0. We are only worried about the result of this if we get a root of I. If there are any real terms on there as well, then we would have e to the something times the cosine or the sine. But you'll see with this, our roots will be negative b over 2, so negative 1 plus or minus the square root of b squared, so 4 minus 4ac, which is minus 8. This is 2I over 2, which is I. And so our roots for yc will be e to the negative t cosine t plus e to the negative t sine t. And of course, we need a c1 and a c2 outside of that. But really, we don't need any of this because we've just found that we're good with what's up here. And what I mean by that is that our guess for y particular, so ypg of t, can just be a cosine t plus b sine t. Finding y prime pg of t will just give us negative a cosine t plus b cosine t, and by cosine over here I did mean sine. Y double prime pg of t gives us negative a cosine t minus b sine of t. Plugging all of this into our y double prime, our y prime, and our y, we will get negative a cosine t minus b sine t plus or minus 2a sine t plus 2b cosine t, and I'll do a little rearranging here already, plus 2a cosine t plus 2b sine t, and all of this is equal to 4 cosine t plus 2 sine t. So I already grouped these variables in a way where we can just combine the like terms that we do have. We'll be left with 1a and 1b over here. So now setting our like terms equal, all of our cosines, that'll be a plus 2b is equal to 4, and then all of our sines, negative 2a plus b is equal to 2. We can make an augmented matrix out of this. 1, 2, 4, negative 2, 1, 2, and solve away. Let's add 2 row 1s to row 2, 5, 10. This will become 1 and 2 after we simplify things down, and we'll subtract 2 row 2s from row 1. So we see that going back up to this, well, it's really our ys, or whatever we want to call it, our steady state solution. Our a is equal to 0, and our b is equal to 2. So 2 sine t, a for question 13, is our solution. Let's find the inverse Laplace transform of this big, scary looking thing. And right off the bat, we should be slightly concerned, first off, seeing this trinomial. In general, we really would like to simplify things down to linear factors. So just having an s by itself is much easier to deal with than having an s squared plus 2s plus 5, until you realize that s squared plus 2s plus 5 is actually pretty special, because we can factor that to, my 5s look like my s's. I have to do this. Alpha plus 1 squared plus 4. And this 4 is nice because it's a 2 squared. So if we end up with a 2 somewhere on the top, or an alpha plus 2, I think. I need to grab the table actually. We will have a pretty easy time. Okay, there's our table, and here's what I'm talking about. We can get our denominator into the form where it works with one of these. It just depends what ends up on top. So for now, what this means for us is that we're going to have to do a pretty annoying partial fraction. So 2 alpha squared plus 5 alpha plus 7, all divided by alpha plus 2 times alpha squared plus 2 alpha plus 5 is equal to some a over alpha plus 2 plus some b alpha plus c over alpha squared plus 2 alpha plus 5. Multiplying our denominator up, we see that a alpha squared plus 2a alpha plus 5a plus b alpha squared plus c alpha plus 2b alpha plus 2c is equal to, if I can fit this in here, 2 alpha squared plus 5 alpha plus 7 plus 5. Okay. Oh, God. We can set our like terms equal, just taking our alpha squareds first. We see that a alpha squared plus b alpha squared is equal to 2 alpha squared. Now just using our alphas, we have 2a alpha plus c alpha plus 2b alpha is equal to 5 alpha, and then our constants 5a plus 2c is equal to 7. I'm going to make a matrix out of all of this with an A, B, C column, and then the value it's equal to. We have 1, 1, 0, 2 coming from here because we have no C's in here, so we have a 0 in that position. Then 2, 2, 1, 5, and finally 5, 0, 2, 7. I'm going to copy this over in case I make any mistakes, and I think we're actually going to go down into this other problem to solve this. We generally need a lot of space on these questions. So this 1, 1, and 2, 2 are looking good. So we're going to subtract 2 row 1s from row 2. That will give us 0, 0 minus 4 here is 1. Let's subtract 5 row 1s from row 3. 0, negative 5, negative 3. What now? Let's subtract 2 row 2s from row 3. 0, negative 5, so this becomes 1 and 1. And let's subtract a row 3 from row 1. 0, 1. Okay, that's a little boring, but in the end, we get 1, 1, and 1, so that means we can rewrite. That's interesting. I think I'm going to leave that in there. I think that's the first time I've ever sneezed on recording. Isn't that exciting? Okay, so we can rewrite this whole thing, and now there's something in my eye, as 1 over alpha plus 2 plus alpha plus 1 over, remember how I said we could rewrite this denominator to begin with, alpha plus 1 squared plus 4, which is better written as 2 squared. Okay, we are almost done. We know right off the top of our heads, don't even need to go look at that sheet, that this will be that the inverse Laplace transform of this is e to the negative 2t. Let's see, I need to go rearrange this. We're gonna go all the way down here. We know that the inverse Laplace transform of this first bit, so we're forming a f of t here. This is e to the negative 2t because the a value in that is subtracted on the bottom, e to the at. Okay, and then secondly, we see that this is in the form. We have the second term in the form s minus a for a equal to negative 1 and b equal to 2. So if a is negative 1, our inverse Laplace transform will give us e to the negative t cosine 2t. And looking up here, we see answer choice B for 14 is correct. Question 16, if y of t is the solution to this initial value problem here, then what is y of t? So we need to take the Laplace transform of both sides of this equation here. Y double prime, I'm going to make this small for just a second. Y double prime will become alpha squared y alpha minus alpha times y at 0 minus y prime at 0. Well, all of our initial conditions just go to 0, so we don't really care about that. Plus 2 alpha y alpha, and then another initial condition term that doesn't matter, minus 15 y alpha equals the Laplace transform of delta of t minus 1. So that will become e to the, let's see, minus c, e to the negative alpha, like that. Let's factor out a y alpha times the quantity alpha squared plus 2 alpha minus 15 minus 2 alpha minus 15 plus 2 alpha minus 15 equals e to the negative alpha. So y alpha is equal to e to the negative alpha all divided by alpha squared plus 2 alpha minus 15. We can factor that to alpha plus 5 alpha minus 3. Let's do some partial fractions on this. We can set this guy equal to a over alpha plus 5 plus b over alpha minus 3. And just to make things a little more clear, let's factor out our e to the negative alpha at this point. So we have 1 over 1 multiplied by e to the negative alpha, like that. Multiplying our denominator up, we will see that a alpha minus 3a plus b alpha plus 5b is equal to 1. So a is equal to negative b because of our alpha terms, and negative 3a plus 5b is equal to 1. So from here, now that we have an equation for a and b, we can set up a matrix 1, 1, 0, negative 3, 5, 1, and solve for a and b. I'll just make a copy over here. 1, 1, 0, negative 3, 5, 1. Let's add 3 row 1s to row 2. That will give us this is a 3, this is a negative 3. So we add 3, that gives us 0, 8, and nothing else. So we get 1/8 and negative 1/8. So now that we have our values for a and b, we can go and rewrite our y of alpha as 1/8 e to the negative alpha multiplied by negative 1 over alpha plus 5 plus 1 over alpha minus 3. And at this point, we are ready to solve. We know that e to the negative cs, in our case c is equal to 1, the inverse Laplace transform is the normal inverse Laplace transform of everything multiplied by e to the negative cs, but we replace all of our t's with t minus that c value, and then everything is multiplied outside by uc of t. So we will have y of t is equal to 1/8 e to the negative alpha will become u1 of t multiplied by negative e to the negative 5 t, but our t is replaced with t minus 1, and then plus e to the 3 t minus 1, end bracket. And that corresponds with answer E for 16. Whoops, gotta erase all this stuff. Actually, I'll just move it if I can select. There we go. Okay. 17, let's find this Laplace transform. We have e to the t times something we're familiar with, an integral from 0 to t of some function of tau times some function of t minus tau. So we have to use the rule on the outside here that the Laplace transform of anything multiplied by e to some constant c times t, that's right here, will just give us the normal Laplace transform of f of t, but we replace all of our t's with t minus c. So what we can do here is treat this Laplace transform like we're only dealing with this integral here, and then at the end replace all of our t's with t minus 1's. So the other rule that we were just talking about that we're going to be dealing with is this one right here. Our f of t minus tau in this case is cosine of t minus tau. That's an especially bad tau. And then g of tau is sine of tau. And we're told that the Laplace transform of this will just be the Laplace transform of sine of t. I'll turn all of our taus into t's in a sec. So we have g of t is just sine of t, and f of t, which is what we need to find to take the Laplace transform of to find f of s, is just cosine of t. We unsubtract that tau. So at this point, all we'll be doing is taking the normal Laplace transforms of sine of t and multiplying that by the Laplace transform of cosine of t, and then replacing all of our t's with t minus, not t's, all of our alphas that we'll get with alpha minus 1's. So let's do that. The Laplace transform of sine of t is 1 over alpha squared plus 1. We're multiplying that by alpha over alpha squared plus 1, which is the Laplace transform of cosine of t. This just gives us alpha over alpha squared plus 1, and then we need to replace all of our alphas with alpha minus 1 over alpha minus 1 squared plus 1. That is option. Oh, yeah, whoops, we multiplied our denominators as well, so we do get a squared on the bottom. That was a a silly mistake, and I hope you caught me on that as well. Okay, 18. We're out of Laplace land. Finally, let's consider this system. Find all the values of a such that the origin is an asymptotically unstable spiral point. So the origin is an asymptotically unstable spiral point whenever we have a positive, I don't want a text box, positive real part of our eigenvalues and a conjugate imaginary pair. The imaginary bit contributes the spiral, the rotation factor, and the positive real part contributes to the increasing values as time goes on, away from the origin. So all we need to do is solve the determinant of a minus lambda I equals 0. That's negative lambda times alpha minus lambda plus 16 is equal to 0. We get alpha squared minus, that's not alpha, lambda squared minus alpha lambda plus 16 is equal to 0. Running this through our quadratic formula, we get negative b over 2, so alpha over 2 plus or minus the square root over 2 of b squared, so alpha squared minus 4ac, which is minus 64. We see that for all alphas greater than 0, we get our positive real part, and for all alphas less than 8, we end up with an imaginary part here. So alpha between 0 and 8, D is our answer. X of t is a solution to this initial value problem. We are finding x of 1. Finding our eigenvalues, we'll be solving 3 minus lambda times negative 1 minus lambda plus 4 is equal to 0. Alpha squared minus 2 alpha minus 3 plus 4, so plus 1 is equal to 0. This is alpha minus 1 squared is equal to 0. Alpha is equal to 1 with a multiplicity of 2. Plugging that into a minus lambda I, we get 2, 1, negative 2, negative 4. We can simplify this down to 1, negative 2, 0, 0, and extract an eigenvector of 2, 1 out of the deal. Now, since we have a multiple eigenvector and we've only found one eigenvalue, we're going to solve for the generalized eigenvector, which we get by setting up the system of a minus lambda I, so 2, 1, negative 4, negative 2, and setting that equal to our first eigenvector. We can simplify this down as 1, 1, negative 2, 1, 0, 0, 0. And once we have these four components in the same form as they were when we solved for this first eigenvector, whatever we have on the right side is our generalized eigenvector. So our generalized eigenvector is 1, 0. Now putting together our solution, x of t is equal to c1 v1, 2, 1, e to the lambda 1t, which is just lambda 1t, plus c2 times lambda 1 t plus lambda 2, our generalized eigenvector. No, I keep saying lambda when I'm not supposed to be. This has been a very long exam for me. There are so many bad takes in here. Plus 1, 0, that's our generalized eigenvector. Nothing to do with lambda. E to the t. We're given an initial condition that x at 0 is 1, 0. So we can set 1, 0 equal to c1, 2, 1 plus c2, 1, 0, because this 2, 1 term is multiplied by a t, which will go to 0. Solving things in a matrix form, we have 2, 1, 1, 0, 1, 0. We can subtract 2 here. We see that c2 is equal to 1, c1 is equal to 0. So I'll go back up, not sure why I decided to erase this. We go back up, delete our c1 entirely, replace our c2 with a 1, and we are evaluating this at 1. They want x at 1. So x at 1 is 2, 1 plus 1, 0, so 3, 1 e to the 1. So 3e and e. A is our answer for 19. Oh God, I forgot we had such a bad, not bad, but time-consuming problem as the last one. Okay, we have phi of t, that's the fundamental matrix for this homogeneous system, and we're trying to find a particular solution to this non-homogeneous system. Oh God, here we go. So this particular solution, xp, is given by, if I can remember correctly, phi of t times the integral of the inverse of phi of t multiplied by this guy right here, I'll call it g of t dt. And someone left a comment on one of my videos, I think it was earlier today, talking about how, it's probably more correct to be using a different variable in here. So replacing all of our t's with s's, and this might, in some other world or some other formula that works for this, be a definite integral from 0 to t ds. But for the intents and purposes of this video, this works. This will give you your correct answer. So it's what I'm going to use now. Let's find the inverse of phi of t. So phi of t inverse is equal to 1 over the determinant of this matrix, which is, let's see, e to the 4t plus e to the 4t, so that's 2e to the 4t. We will flip or switch the positions of the a and d values, so e to the 3t, e to the t, and switch the signs, e to the t, negative e to the 3t, of our b and c positions. And at this point, we are ready to start slogging through all of our computation. In fact, before I put a determinant down, an integral, let's compute this guy, our inverse, multiplied by g of t, which is just 4 e to the t. This gives us 1 over 2 e to the 4t, and in here we get minus 4 e to the 4t and 4e to the 2t. So dividing out our 2e to the 4t, both of these will become coefficients of 2, and then here we'll just end up with negative 2, and here we'll end up with e to the negative 2t. So now all there's left to do, actually it's a lot, is take the integral of negative 2 to e to the negative 2t dt. And one of the reasons that whoever left this comment has a good point is that, there are c's that should pop up in here. Like, we should have some unknown constant terms after this integral, but it only works if we don't. If we just, shut our eyes and close our ears and just go along with it. So we're going to drop those c's. Negative 2t and negative e to the negative 2t is our slightly sketchy answer there. Now grabbing our fundamental matrix, e to the t, negative e to the t, e to the 3t, e to the 3t, and multiplying it by negative 2t, negative e to the negative 2t, we will get, theoretically, an answer. It's going to be a 2-by-1 matrix. We will have minus 2t e to the t minus e to the t. Then down here we'll get 2t e to the t and minus e to the t. Factoring out an e to the t, we are left with negative 2t minus 1, 2t minus 1, e to the t. And that is option D for 20. Okay, this this was not a very fun experience going through this exam, but it's a very good practice for me. I have my midterm on Thursday, so I hope it went better for you. And I don't know, it's going to be a late night.